So in this one, H17, what is the wavelength of a photon given off by a nickel nucleus when it drops from the 2.158 megaelectron volt level to the ground state? If you want to pause the clip and give this a try, and then when you got that, you can hit play to continue. Okay, so we see here we can convert a value to joules. Find the frequency, 5.212 times 10 to the 20th hertz, and the wavelength of this is 5.76 times 10 to the negative 13 meters, and that's this transition from the color we can see from here to here, right? What could have happened though, it could have gone from here to here, then from here to here, right? So you'd actually have two separate gamma rays. We'd subtract this value from this value, figure out what kind of photon we shove out, and then this value 1.322 down to 0 would be two gamma rays instead of one gamma ray there. So the different radiations cause different kinds of ionization, and here's a picture of alpha radiation there at the top, and it causes ionization there, beta radiation, gamma, and neutron. And so what happens with ionization of radiation with matter, an alpha particle could come in and essentially it can interact with a proton or with an electron and cause the electron to escape an atom. And so what happens is these electrons get knocked out, and knock electrons out of the atoms in the air, and depending on their the type of radiation, will have different effects. And so if we look at this graphic here, this is an important one here to look at the different types of radiation. Let's take a look at an alpha particle. We know it's a helium nucleus, positive 2e of charge. We have the mass, penetrative power. So this can go through a few centimeters of air. As soon as you get beyond that, it's not going to go any further. Now, how many ions per millimeter of air for 2 megaelectron volt particles? It can ionize 10,000 atoms, which is very significant, right? And again, only through a few centimeters of air. And so here's some of the ways to detect this. The fluorescent effect there, effects for photographic film. And it's affected by magnetic electric fields, right? So you have alpha particles that, can be deflected by electric and magnetic fields based on, the right-hand rule for magnetic fields, and then electric fields, positive and negative sides. Beta particles, fast electrons, right? So negative E charge, we have very small mass. It can go through a few millimeters of even metal. So alpha particles can go through air. But beta particles can actually go through metal and ionize 100 ions, make 100 atoms ionized per millimeter with a certain amount of energy there, and we can detect them these ways as well. And then gamma rays, right? No charge, no mass, but it can even go through lead, many centimeters of lead. And it's just going to do one because it's one photon. It can ionize one atom, and then this is the effects that we can see with those. So in detecting radiation, a chamber is filled with gas and is ionized by the incoming radiation. The ions go to the casing, and the electrons go to the positively charged electrode. And so as an atom is ionized here, we'll have that transfer, right? One is we'll have the electron going one place, and then the actual ion going to the other. And in this case, the ions go to the casing, and electrons go to the cathode, and it'll go to the counter and record an event. Okay, so as we evaluate what's happening with protons and neutrons and atoms in terms of their stability, this is called a surge plot, and there are about 2,500 nuclides, and only about 300 are stable. And if you look at those those are the dots there, the stable nuclides are here, and so you can see these dots in here. Those are stable nuclides. So the rest are not stable. Stable nuclei generally have more neutrons than protons, and with more protons, there's electrostatic repulsion, right? And so that should make sense. As you get, the proton number versus neutron number here, you get too many protons, the electrostatic repulsion is increasing, and you have a less stable atom. And then if you have too many neutrons, it's going to favor decaying into protons, and so those will start to decay. And so besides these 300, all the rest of these nuclides are going to undergo decay. Alpha, beta, beta positron, beta minus decay, and there's a pattern. So you have the different nuclides, and they're going to follow this pattern where, and we'll see that as we go, but they'll alpha decay, and then they'll be ready for a beta decay, and then another beta decay, and then maybe another alpha decay, and it'll just keep staying unstable, and then maybe get to a stable, position. But yeah, again, most nuclides are unstable. And so we talk about the table of elements. This is kind of neat here to see this. This is 1869, where we have the elements, arranged in a table based on patterns, and yeah, we have the predicted elements that can fill in the gaps there. If you can see these different places here, these are the known elements, and then like, okay, there must be elements to fill in these gaps, and yeah, and you can see even with the type of organization here, this is just good scientific method where you're trying to organize and trying to come to conclusions based on what you see. So alpha decay equations, we're going to go ahead and practice a few of these here. Let's say we have radium to radon. We have the beginning of the equation here. Go ahead and finish the equation for this, and go ahead and finish the equation for this, for polonium to lead. And so yeah, go ahead and pause the clip and give that a try, and when you're ready to check, you can hit play to continue. Okay, so afterwards we have radon, and then we have our helium nuclei with 4 nucleons, 2 protons, 2 neutrons, and then possibly an alpha or possibly a gamma ray that's shot out as well. And again, that depends on how excited the nucleus is, through that decay. For polonium to lead, we should have 20882 with the alpha particle. This is the symbol alpha for alpha. You can either have He for the helium nucleus or the alpha particle there, and then possibly gamma ray that shoots out as well. So again, about the neutrino, it's a subatomic particle, like an up quark or down quark. And then again, there's evidence that it has a very, very, very small amount of mass. It's not significant. All right, so as we consider alpha radiation or alpha decay, we have, in this case here, radium to radon, and this alpha particle shoots out. And there's a couple of different ways it can shoot out. It can shoot out to where, the nucleus shoots out the alpha particle, transitions all the way down, and the alpha particle itself has this much energy here, 4.745 mega electron volts. Now, it's possible that instead of that happening, we have the alpha particle shoot out, but it has less energy. Therefore, the nucleus is still in an excited state, and then it will shoot out a gamma ray of 0.186 MeV. And yeah, and so both are possible. The nucleus itself, just based on the probabilities of decay, will have different types of decay. So let's take a look at beta minus now. We have lead to bismuth, and we have thorium to protactinium. So go ahead and pause the clip and write out the equations for beta minus decay here. Give your best shot with that, and when you're ready to check, you can hit play to continue. Okay, so we should get the one less or one more proton here, so 80 becomes 83. Therefore, we also have an electron that shoots out for conservation of charge. You get one more proton. We'll have to have an electron to keep neutral. We can't just gain charge out of nowhere. And then remember, with an electron, we have an anti-neutrino that's produced as well, and for conservation of energy and conservation of momentum that shoots out. So for thorium protactinium, we have 91, being, going from 90 to 91, another proton. And then we have the electron being produced, as well as our anti-neutrino that shoots out. All right, how about gamma decay? If we write out the equation, we have a little star here to represent an excited nucleus, uranium nucleus. What ends up happening with this is you just write out uranium. Nothing changes with the nucleus except that it goes down in an energy and shoots out a gamma ray. And we see that here. All right, so let's take a look at this one here. We have magnesium nuclear energy levels, and this is magnesium nucleus with the different energy levels here. And so, after decay, let's say that, the nucleus is in an excited state. And what's shown here is that it's going from an excited state of 5.24 mega electron volts, and then it shoots out a gamma ray, and it goes from 5.24 to 1.37. So if that happens, then the next step would be it would go down here and then would shoot out another gamma ray, and in that case there 1.37 to 0. This would be a 1.37 mega electron volt photon. This one here we would subtract 2.54 from 1.37, and that would be the energy of this photon. So if we take a look at this one here, this is H18. What frequency of gamma radiation will be released after alpha decay, going from 0.307 mega electron volts to the ground state after the reaction? And so, yeah, let's go ahead and try that. And I'll let you pause the clip, and you can go ahead and calculate that. Again, that's for this case here where the alpha particle shoots out, going from 4.983 to here. So the alpha particle itself, let's go ahead and calculate that real quick. We go from 4.983 to 0.307. So that would be a 4.676 mega electron volt photon that shoots out. And yeah, and then after that, the nucleus can drop down to the ground state and shoot out a photon equal to 0.307 mega electron volts, and so we can get that. And here, I don't know if I mentioned, this is, I may have misspoken, this is an alpha particle shooting out, not a photon, right? So this is an actual alpha particle, 2 protons, 2 neutrons, right? 2 protons, 2 neutrons shooting out with this much energy, and then the nucleus shoots out a photon, which is light, and with this much energy. So go ahead and pause the clip and calculate with the frequency of this radiation that shoots out, the 0.307 mega electron volt photon that shoots out, and go ahead and do that. Okay, so we convert to joules there, and we'll get a value of 7.4 times 10 to the 19th hertz. So very energetic photon of gamma radiation that shoots out. The wavelength therefore would be 4.046 times 10 to the negative 12 meters.